Right, folks. Today, with a new setup, as you can see, my background has changed. I'll be starting a new topic, and the topic is electromagnetic induction. Oops. Electromagnetic induction, which is EMI. Electromagnetic induction is actually based, or you can say it comes from a mixture of Faraday's law and Lenz's law. However, today, instead of just jumping into and talking about electromagnetic induction like Faraday's law and Lenz's law, what I want to do is give you a feel for what electromagnetic induction is, and instead of like introducing the topic, I'd go the other way around. And the first things first, I will just give you some examples of how these induction things work. As if you hold a sheet of paper, then what's the experimental conclusion that comes after it? Then, after that, we'll be discussing about Faraday's law and Lenz's law in later videos in this playlist. So, without a further ado, again, let's start off by defining electromagnetic induction. If you define electromagnetic induction, it's like electromagnetic induction flux is directly proportional to magnetic field, and again flux is directly proportional to area. Flux, the magnetic flux that we have, which is a byproduct of this thing over here, magnetic flux phi of B, is the number of field lines, magnetic, not electric, magnetic, passing perpendicular to a surface, right? Which means if you want to see how this definition, like definition 1 implies, would be if I take a sheet of paper, oops, I have slipped, and if I draw magnetic flux over here, say these are flux, right? As if theta b is equals to 2, and this represents magnetic flux, and this is our area vector, and this is our sheet that we colored. So magnetic flux, the number of field lines magnetic passing perpendicular to the surface, which is shaded in green line with a square white shaded in green line with square boundary with white color. Then magnetic flux, so literal definition is like the number of field lines passing through a surface. If you take stronger magnetic field, then what would it imply is, say this is my square, and I will increase the number of flux passing through the surface, that is magnetic field lines, then phi of B would be, say, 3, which means as you increase the number of magnetic field passing through the surface, which is of same area that we had earlier, then we will end up having more magnetic flux. That is, we will have more number of magnetic field lines passing through the surface. So that is one way to increase magnetic flux. Remember, as I'm talking about magnetic flux over here, um, it's different magnetic flux is not electromagnetic induction. Well, electromagnetic induction comes after magnetic flux, as if the equation of electromagnetic induction includes magnetic flux as one of its component that we compute, which is electromagnetic induction. If you talk about is total number of the difference, like difference in magnetic flux with respect to time. So to get to this point first, we need to understand what magnetic flux in itself is. This is not the idealist of equation, but to have a mental map, you should know that it is some change, and by the change we induce something. Literally, induction is inducing something that we do. Right. Now, coming back to our topic, there is another way to have stronger magnetic flux. That is by if we increase the surface area. This is not quite the representative area. I should take a bigger area. This is much better. Well, then let's say phi would be b equals to 4. Then flux itself is dependent on magnetic field. As you can see, if we increase the number of magnetic field lines passing through the surface, the flux gets stronger. At the same time, flux is also induced by area, which means if the surface area that we take into consideration gets bigger, then the flux lines passing through the surface increases, right? So this is like the general idea of flux, which is kind of an abstract idea in physics itself, but the reason why we define flux at the first place is because we just can't measure anything without any difference, and we have to constrain things in physics to get an idea of something. To give a better analogy, say we are computing potential energy of moving one body to another place. Say from this is Earth, and I want to move it to h height above. So what we compute while we're computing this potential field is the change in potential field from potential energy from moving this pen from my left hand to my right hand, which is the height. Why it is important, why it is relevant in most of the cases is again because we just can't compute absolute values. All we do all the time in all of physics is computing change. And to compute change in terms of field lines, say especially in terms of magnetism, electricity, and anything that includes field, flux is the way to go. So flux comes from the place that is, we can never compute the absolute value. So what we can compute elsewhere is the change. And that's also the reason why we have induction or electromagnetic induction due to change over time. So this means the magnetic flux would be BA, right? But this is extremely simplified equation. If we include the angle, say the surface is inclined at some angle, then the equation becomes B dot A. Now, dot product. Whenever we talk about dot product, we get a scalar value whenever computing dot products. Why is the case? Because you have to know there is no such reason as why, but know that dot products and scalar products and vector products exist to tell us about how bodies move in this universe. For example, choppers, wings, or fangs, or whatever you call it, moves in one plane and the motion is in another plane, right? How would you define that equation? Cross product. But if the motion is in one plane and the other motion that we take into consideration is also in the same plane, then it's irrelevant to compute direction in these cases, because at the end of the day what we're trying to achieve is the motion, and the mathematical foundation has already thought about these problems, and dot product solves that problem. That's why we use dot product over here. So yeah, that was the philosophical idea, mathematical idea of having dot product with an intuition. Also, in this problem, as we know, and if you don't know, that the area in itself is a vector product. It's not a scalar value, which means if we take a surface, say this is our, let me change colors. If this is our surface, then the area vector perpendicular to the surface would be facing outwards in the left of this face, right? This is the vector product, vectorial representation of area vector in this problem. Yeah, we know that it has to be like perpendicular. The surface, when we define the magnetic flux, the number of field lines magnetic passing perpendicular to a surface, but when we write the same thing in equation, we have to be abstract and rigorous. And in that case, even though the definition says that perpendicular, the area vector itself is parallel to the magnetic field, and that's why we have B dot A, which is BA cosine of 0 degrees, and it becomes BA, which is magnetic flux in these cases. Now, if we take this surface, right, and we say move here, then, and if we tilt, so I have to make it again, never mind. No, this is not the right face that I was looking for. If we say tilt the face in a way that the vectorial symbol of magnetic flux comes outwards and magnetic field is in this direction, then at first glance it might look like, hey, this is perpendicular to the field, but no. The problem with this equation is, since we mentioned that the area vector is coming outwards and the magnetic field is going in x to y direction, but the area vector is coming from, say, y to z direction, these are perpendicular, which means BA would be cos 90, because we are looking in terms of not the surface itself, the vector, and phi B would be 0. So it's just an idea that you have to know that area vectors exist and magnetic fields exist. And if you know what's happening in these cases, then it should make sense, right? Again, another example that I want to take would be, say, if this is the surface, and if this is the surface, and we have this magnetic field B, which is going at some direction to the area vector, which is perpendicularly outwards, then this becomes theta angle, right? And B is here, then phi B would be B dot A, which is B vector dot A vector, and BA cosine of theta. Because cosine again comes from this place as we projected down B on the surface A or A to the surface B, it's going to be cosine of theta. It's all about projection. Again, dot product in physics especially talks about projection. How are you projecting and how are you defining motion if it is not inclined, and how would it be inclined? It's just a mathematical tool that explains this phenomena. That's why you see it all over the place. Right. Then phi B is equals to B dot A. Which is the magnetic field. Again, by definition, the number of field lines magnetic passing perpendicular to a surface is the magnetic flux. Right? Now, SI unit of magnetic flux would be Tesla, and A is meters per second square, then it would be Weber, right? Which is again a scalar quantity. Now, this was all the prerequisite for, say for electromagnetic induction. And to understand electromagnetic induction, you should have this basic idea about how magnetic flux at the first place works. I hope this was a good introduction, or maybe a prerequisite to the course. And I will continue this video, and we will talk about Faraday's experimental observation in next video, and continue electromagnetic induction afterwards. So, thank you.